Hello, let's prove that this is a perfect substitutes utility function. Once again, here's our utility function, and we want to prove that it is a perfect substitutes utility function. Recall, for a perfect substitutes utility function, the marginal rate of substitution is constant, meaning the slope of the indifference curves are constant or downward sloping straight lines. Before we get started, we need to review the derivative of a natural exponential function. That's what we're dealing here with this utility function. So here we have a natural exponential function. Y is a function of x. And to take the derivative of this with respect to x, we're going to look what's in the exponent here and take the derivative of that. So we're going to have that down in front. So this is just the derivative of this exponent, this g prime of x. And then we're just multiplying it by the unchanged exponential function, the original exponential function. So with that, let's get the marginal utility of good x. We're going to take the partial derivative of this utility function with respect to x, and I'm just following again this rule on top here. So taking the derivative of 2x plus y with respect to x is just 2. That's why I have a 2 down in front. And then we just multiply that by the unchanged natural exponential function. To get the marginal utility of good y, I'm going to look at the exponent here in the utility function and take the partial derivative of what's in the exponent with respect to y. So the derivative or partial derivative of y is just 1, so I don't have to write anything down in front here. And then that's just multiplied by, again, the unchanged natural exponential function. Writing our results once again, and now let's form the marginal rate of substitution, which is the marginal utility of good x divided by the marginal utility of good y. So putting those marginal utilities into this formula, you'll notice this cancels very nicely to just equal 2. So the marginal rate of substitution is constant. It always equals 2. This is a perfect substitutes utility function. This consumer is always willing to trade away 2 units of good y for 1 more unit of good x, holding utility constant. Let's derive the equation for an indifference curve. Let's set utility equal to e raised to the power of 10. So setting utility equal to e raised to the power of 10, we're going to find various combinations of x and y that give the consumer a constant level of utility, which is roughly equal to about 22,000. So I'm going to take the natural logs of both sides of the equation. And so the natural log of e raised to the power of 10 is just 10, and the natural log of the right-hand side of the equation is just 2x plus y. We're going to solve this for y, and y equals 10 minus 2x. And you'll also notice that the slope here, minus 2, is just the absolute value of the marginal rate of substitution. And if we wanted to come up with some various values of x and y that give the consumer exactly e raised to the power of 10 units of utility, we could form a table here. And so if x is 0, plugging that into our indifference curve equation, if x is 0, y is 10, that is a combination that gives us a utility of e raised to the power of 10. Another combination is when y is 0 and x is 5, plugging those values into the utility function. Once again, utility is equal to e raised to the power of 10, and we could do a bunch of different examples here, and that is our indifference curve, okay, where e is raised to the power of 10. Let's go ahead and graph it. So the indifference curve where y equals 10 minus 2x, that's this line right here. Any point along this line gives the consumer a level of utility equal to e raised to the power of 10. And just for good measure, I put in another indifference curve here. This indifference curve here with a vertical intercept of 4 and a horizontal intercept of 2 would correspond to an indifference curve where utility equals e raised to the power of 4. Okay, that's it.